Good morning, students. Today we will formally start the Algorithm 1 course. Um, as you have already probably noted, the modus operandi of the course that was discussed by Professor Pawan Goel in the previous lecture. So we will follow that modus operandi all through the semester. And as you understand that this is one of the fundamental courses in computer science, and therefore we have to understand uh, like in very explicit details about this course. We would try to help you from uh, our side to the best extent possible, but your cooperation is also required. So every time you observe a lecture, please note down the issues that you face, the problems that you are facing in understanding, and let myself or Professor Pawan Goel know about these problems. Also, keep your TAs informed, so they are always there to help you. So if there is any specific issue that you feel that you are not understanding, you can directly write to us, jot down the points, and then share it with us in a more organized fashion. Also, we will have interaction sessions where we will have one-to-one discussions to solve your doubts. We would now formally start off with the course, and I would share my screen so that I can write on it and we can proceed with the lecture. So I hope my screen is visible to all of you. Um, so this course, as you will see in the curriculum, is named as Algorithms 1, and primarily I will be following the textbook written by Richard Neapolitan and Kumar's Naimipur. The title of the book is Foundations of Algorithms. So this is the primary textbook that most of the time I am going to follow, but there are certain things that I'll be teaching which will not find in this book, and for those we will be providing you with reference materials time to time, and also you will find lot of other tutorials and video lectures on YouTube and Google if you do some simple keyword search. So let us start with some basic things today. So as you understand, the uh, name of the course is Algorithms 1, and therefore the first task that we have in hand is to to define succinctly what an algorithm is. So basically the question that we ask is, what is an algorithm? Okay, and whenever you uh, you know uh, observe such a question, many different types of answers actually pop up. But like if you want to, accumulate all of these into a very crisp definition, then something like the following would typically tend to emerge. So this is a nothing but a step by step technique to solve a problem. Now mark the word problem. So algorithm in a nutshell can be defined as a step-by-step technique to solve a particular problem. Okay. Now the question is, what is a problem in the first place? So do we have a succinct definition of what a problem is? So in order to, define algorithm correctly, you have to first define a problem. So a problem is a question, okay? It is a question to which we seek an answer. Okay. So basically, a problem is defined as a question to which we seek an answer. To be a little more precise, let us take an example. So the following is an example of a problem. Determine whether the number x is in the list S of n numbers. Okay, so this is the question part of the problem. Okay. Similarly, the answer of this would be either yes or no, depending on whether x is in S or not, right? So this is a typical example of a problem. Okay. So, and I guess from your programming and data structures courses, you have already identified that this is the famous search problem. Okay. So you are trying to search a particular number or a particular key X in a list S containing n numbers. Okay. Now there are a few things to observe when we talk about a problem, there are a few things, few important things to observe. The first thing is what we call parameters. So what is a parameter? So these are specific variables parameters are specific variables, okay, that are part of the problem and do not have a value assigned to them. So the search problem example that we saw just now, there the parameters are S, that is the list of elements, N, that is the size of the list, and X, that is the key which we wish to search for in S, right? So these are the three different parameters of the search problem. Similarly, for any specific problem, you can have one or more parameters, and these parameters typically do not have a value assigned to them. Now, the next important issue that we need to resolve is variables or parameters, okay, when they assume a value, okay, when variables or parameters assume a value, then this becomes an instance of a problem. Okay, so let us understand the difference here. So problem is something that is generic and has a bunch of parameters. Once you have set the values of these parameters, this becomes an instance of that problem. Okay, so a problem is something that is much more generic. Whenever you assign values to the different parameters of a problem, it becomes an instance of that problem, which is a more specific thing. Okay, now the last in this list is what you define a solution to be. Okay, a solution is an answer to a specific instance of a given problem. Okay, so Then we have, let us once again go back. So we have now a few things on our plate already. Algorithms, okay. This is a problem solving technique. A problem has parameters, okay. These parameters on having values, okay, become instance of a problem, and you can posit a solution to a particular instance of a problem, which is nothing but the answer to that instance of the problem, okay. So these are some of the very basic ingredients that you need to keep in mind when we are analyzing algorithms, okay. So after this, we will try to write a very simple algorithm for the search problem that we have discussed just now. So I guess all of you are aware of the technique for doing such a sequential search. So what we will do, we will start from the first element in S and keep comparing the elements one by one with X unless we either find X in S or the scanning of the list is over. That is, we have exhausted scanning. We have exhausted scanning the list. Fine. So, in this course, we will be using pseudocodes to write algorithms, okay. uh, and these will be more or less like the C style pseudocodes. So these are pseudocodes which would be not so difficult for you to understand, because most of it would look like the standard C syntax, okay. Okay, so the sequential search, let us write. So we have written the sequential search algorithm in plain text. Now let us write it in a little more formal way. So first, what is the problem here? The problem is that is the key X in the array S of n keys. This is the problem. Input a positive integer n, array of keys S, indexed from 1 to n, and a key X to search for. Okay, so this is the input. The output is a variable, let's call it location. Okay, that is the location of X in S. This is set to 0 if X is not found in S. Fine. So, formal description of the sequential search algorithm can be written as the following function. Note that we are passing the location variable as a pointer, and we will be using the index data type in order to indicate the index of a particular array position. Okay, so in the general C syntax, you have been typically using an integer to uh, refer to an index, but here, just for a better disambiguation, we shall be using the index data type to indicate the case of index variables or index locations in an array. So the code is very simple. We set location to 1 while location less than equal to n and S of location not equal to the search term, you advance location. If at some point in time location greater than n, then location is set to 0, which means we have not found the search item in the array. Data types like the ones that you have been already using in your programming and data structure course, where you have learned about C programming, like int will indicate integer, data type, float is floating point. Okay. Then we will have, at times we will have an indicator variable, which is also called a Boolean variable, which can be either true or false. Okay. And then we will also sometimes use pointers that I have already talked about in the previous example. Okay. So these are very, very standard indicators of syntax that you have also done in your programming and data structure course. So let us take another example. So every time we do a or write an algorithm, we should be very careful that we are correctly specifying the problem, the input and the output. Okay, this is a very, very important practice that you should uh, learn from the very beginning. So let's say the next problem that we want to solve is add an array of integer numbers. Okay. So again, the input to this problem is what? A positive integer n. Okay. An array is indexed from 1 to n, and output, let's call the variable sum, where we store the sum of the numbers present in S. Okay. So now once we have done this, we can write the formal description of the algorithm. Int number of elements okay. So index I is indicating that I is an index variable. Okay, this is a special variable that we are special data type that we are using. In general, in your C programming syntax, you have been mostly using an integer to represent an index, but here for making a better distinction, we will differentiate it from the integer variable. So index is also an integer, okay, but indicating the index positions in an array. Okay. as simple as that. So this is a very simple pseudocode for achieving the sum of the elements in an array. Okay. So there is a reason why we are writing these simple algorithms, because very soon we will start, estimating efficiency of algorithms, where we will use these examples. Okay. The previous example, that is the search example, the this addition example, and one more example that we will see just now will be used in the um efficiency analysis that we will do after this. So the third problem that we are going to attack is exchange sort. I hope all of you have done some sorting algorithms, okay, in your programming and data structure course. We will look at a very, very simple example here, and we will have a separate segment where we will learn different sorting algorithms and their efficiencies. Okay. So the problem statement here is again sort n keys in a list S in non-decreasing order. Okay. So mark the term non-decreasing. Okay. So we are calling it non-decreasing because there might be repetitions of elements. Okay. That's why we do not say ascending or descending numbers. We say, or ascending and descending orders. Rather, we say a non-decreasing order, assuming that there might be cases where certain elements in the list S is repeated. So the input, a positive integer n, array S of keys indexed from 1 to n, output the array is containing keys in non-decreasing order. So the formalization is again very simple. We write a function exchange sort. The number of elements and the array. We define two index variables, as you might recall from your PDS classes. So again, this is a very, very simple algorithm. So what it is doing, it is exchanging Si with Sj. So Si is small and Sj is large. So that is the interpretation. Okay, and uh, the if you go by this particular interpretation, then if Sj is, you know, less than Si, then you exchange Si with Sj, so that the larger number goes later. Okay. So another very simple example that we will do again, um, like I guess all of you have already done it in your programming and data structure course, but still, just for a recap, we will again try to do this problem. So I guess all of you remember matrix multiplication. Okay. Let's take a very simple example. Let's say A is a matrix of this form. It's a 2 cross 2 matrix, and B okay, and C is the product of A and B. Okay. So if you remember from your school days, Cij, that is a particular cell ij of the matrix C, is given by A I1 B1j plus AI2 B2j, right? So uh, this is a very, very simple formula which allows you to actually generalize the concept and get the product of two n cross n matrices. Say you have A and B, each of them are n cross n matrices, and C is equal to A cross B. Then the different elements of Cij can be computed as k equals 1 to n A I k B k j, and this is for all ij between 1 and n. Okay. So this is how you typically compute the product of two n cross n matrices. Now we can, given this formula, we can very easily write an algorithm to find the product of two matrices. So let's say our next problem is matrix multiplication. Again, the problem here is determine the product of two n cross n matrices. Input a positive integer n two dimensional arrays A and B, okay, each of which have both their rows and columns indexed from 1 to n, and the output is a two-dimensional matrix C, which again has both rows and columns indexed as 1 to n, and each cell contains the product terms. Okay, so this is what is the problem. Now, given the formula that we have already derived, we can easily write a formal description. So let's say remember, these are two-dimensional arrays. We will define three index variables here. And then just straightforward implement the formula that we have derived. As simple as that. So in this way, you can, write the algorithm for multiplying two matrices. Okay. So we have already seen the sequential search problem, okay, in one of the previous examples. Now you have probably come across more efficient techniques of doing sequential search. So the immediate thing that comes to our mind when we have to do a sequential search is that, can we avoid, scanning all the numbers one by one from the first element to the last element in S? So can this be somehow avoided? Okay. So this, the idea was simple, uh, that if you have to avoid this, can we think of a phone book analogy? Okay, fine. So, in a phone book, actually, the uh, names, okay, of course, phone books in these days like have become, almost obsolete, but earlier there used to be such big fat phone books, and the task was to find out the name of a person from this phone book in order to make a call. So if you have to search the names, what will you do? You would typically, not start scanning from the first page to the last page. What would you do? You would first go to, the uh, that page where the uh, first letter of the name of a person appears. Say it is John Smith, if the name is John Smith. Okay, so you go to J, and then you do back and forth. Okay, so and then you see O, then you see H, then you see N. So you go back and forth, back and forth, back and forth. Finally you come up to the correct John Smith result. Okay, so rather than, so in this way you avoid the scanning of the entire book. Okay, so this idea is also sometimes called binary search. Okay. This is why, again, one of the very celebrated ways of searching items in an array. However, there is an important uh, assumption that one makes in doing binary search, and that should have been already clear from the phone book example that we saw just now. So this is that the elements in the array are already sorted. Okay, this is an important assumption based on which binary search proceeds. Okay. So now, given this phone book analogy, and that we want to implement a similar analogy to find an element X in a list of elements indexed from 1 to n, uh, we have to write a simple binary search algorithm. So the problem here again is the same as the sequential search. Determine whether X is in the sorted array S of n keys. So remember, here we need the array that we are searching in to be already sorted. Unless it is sorted, it would be difficult for us to implement binary search. In fact, impossible, okay, for us to implement binary search. So again, the input here is an array of elements indexed from 1 to n. So array S of elements indexed 1 to n and sorted, and the search term X. Output location, which is indicating the position of X in S. This is equal to 0 if X is not present in S. So now, given this, we can easily write the algorithm. We will again define 3 index values. Low, high, and mid. We will set low to the beginning of the array, high to the end of the array initially. Okay. Now we will also set location to 0. While low less than equal to high and location is 0, you find mid, which is low plus high by 2 if X So I guess all of you are aware that the idea is very, very simple. So what you are doing, you have an array, okay, which is sorted. Now you find out the midpoint. Now you find out whether the element that you are searching for is larger or smaller than the element at the middle of the array. So let's say this is S, okay. You are now trying to compare the middle element of the sorted array S with X. Now if this value at the middle is uh, larger than X, okay, then you don't need to search this part, right? So X should for sure lie in this part. So there could be three cases, so, right? So one is that the middle element is exactly equal to S, at which case you make location is equal to mid, okay? Or it could be that the middle element is less than X. In this case, what you will have to do, you will have to search for X in the right hand side, okay. And if the middle element is greater than, sorry, so if X is less than the middle element, okay, then you will search the left side, okay. The right side need not be searched because you have already known that X is not larger than the middle element. And if X is larger than S mid, okay, then you can discard the left side and go to the right side and only search the right side, okay. So this way, what happens is that every time you reduce your searching space, okay. Initially you divide into half, then again you divide into half, then again you divide into half, and you keep on doing this. So every time the array size that you have to search for becomes one half of what it was earlier. So in this way, you can either exhaust all the searching options, or you at some point find out the location, okay, the exact location of X. So we will stop here today, and in the next class, we will look into the idea of analyzing the efficiency of these kind of algorithms. We will look into a little bit more details and move forward toward analyzing efficiency.